and welcome to this lecture. So far, when we have studied varieties, we have, among other things, looked at their tangent spaces, and they have given us some information about, say, the smoothness of the variety. But as you might guess, having a variety, you shouldn't study the tangent space at a point P independently for each P. Rather, these tangent spaces should be seen as instances, or indeed fibers or stalks, of a sheaf of tangent spaces, namely a tangent sheaf or a tangent bundle. And this is the construction we will look into today. So remember that there was a lecture on Kähler differentials, so you can go back to that if you want to refresh your memory or just go through the summary. The module of Kähler differentials was defined for an algebra S over a ring R, so in a rigid affine setting. And it was defined as the pair omega SR, which is an S module generated by symbols ds for each S and S, subject to the derivative relations, and a derivation from S to omega S, what are defined by S maps to ds. It can also be defined after proving that it exists by the universal property that for any S module M and R derivation d prime from S to M, there is a unique S module map from omega S over R to M such that d prime factors over F via this universal derivation d. Yet another characterization of this module is by observing, as we did, that it is the quotient of I delta mod I delta squared, where this quotient space is constructed from this ideal I delta, the kernel of the multiplication map from S tensor S to S. So S is an R algebra. This means that we have a map from S tensor S to S that maps A tensor B to the product AB. And it works like this on pure tensors and is extended by linearity. The reason we are interested in these Kähler differentials is that we can take the fiber, so to speak, or tensor with K, and then we see that what we get is exactly the tangent space, this M mod M squared, or the cotangent space rather, at the point P. So in order to get a cotangent space globally, we need to globalize this into some sort of sheaf. And as things go, we globalize this cotangent notion, and then we define the tangent bundle or tangent sheaf as its dual. So of these descriptions, it turns out that the last one is the easiest to globalize because it's defined in terms of ideals and constructions that are algebraic geometric in nature. So what we want to do is to define the cotangent sheaf of a separated scheme X over a scheme T by replacing this ideal I delta from the previous slide by an appropriate ideal sheaf. If you don't like schemes, most examples we will look at will have X a variety, so a separated pre-variety, X is a variety, and we work over an algebraically closed field. So the scheme T is spec of an algebraically closed field. First, we want to make sense of this ideal modulo squares definition. So we define the conormal sheaf. Namely, if I is a closed embedding of schemes, meaning that X is a closed subscheme of Y, and this corresponds to an ideal sheaf J, as we saw in the previous lecture. So if we have this corresponding ideal sheaf, then the quasi-coherent sheaf J modulo J squared is called the conormal sheaf of the embedding I. So the only thing that needs commenting here is why this is quasi-coherent. Well, J is quasi-coherent. This has been shown. And quotients of quasi-coherent sheaves are quasi-coherent. So we need to see why J squared is quasi-coherent. But this corresponds exactly on affine patches to ideals of the form J squared. So this is this indeed is quasi-coherent. So this is well defined. And then we define the relative cotangent sheaf omega x over t as the pullback of the conormal sheaf of the diagonal embedding of x into x fiber product with x. There were a lot of words here, so let's unpack this. So we have x embedding into the fiber product simply by mapping A to A, comma A. So this is the product of the varieties over K if you're working with varieties. And since the scheme is separated, for example, if you have a variety, then this is a closed embedding. So it corresponds to an ideal sheaf, J. Namely, this is J of x in x times x in t. And this ideal sheaf is a sheaf over the fiber product. If we take it and mod by J squared, it will still be a sheaf over the fiber product. So if this embedding is I, we need to pull back along I to get a sheaf over x. In the affine setting, where x is spec s and t is spec r, then this diagonal map corresponds exactly to the multiplication that we had before. And the ideal sheaf corresponds to the ideal I delta that we had before. And so we get exactly the definition we had before. This defines the relative cotangent sheaf, and we define the relative tangent sheaf as its dual. So both are sheaves of modules. As I just mentioned, in the affine case, then we get exactly the Kähler differentials we had before. One use of this cotangent sheaf is as a smoothness criterion. So let us now restrict ourselves to the case where x is a variety of pure dimension n over an algebraically closed field. Then we denote simply by omega x the Kähler module omega x over spec k. So this restricts to the sheaf corresponding to the modules omega ri over k on affine opens. So these here with algebras in the subscripts are modules, and this is a sheaf of modules. The claim is that x is smooth if and only if omega x is locally free of rank n, where n is the dimension of the variety. So how do we prove this? Both of these conditions are local, and if they are verified on affine open sets forming a cover, then they are verified. So we need to check only an affine open set. So we may assume that x is spec r, and then that it is embedded in some affine space of high enough dimension r. So then if we take a point P in X and we look at the fiber of omega X at P, this will be just the module, so the fiber This will be obtained by tensoring by the field K, which is the residue field of the closed point P in X. But what is this? Well, from our study of Kähler modules, we saw that this is K dx1 plus K dxr, the module vector space generated by dx1 to dxr, modulo the space dfi dxj dxj, where the ideal of X is given by these functions. And so this is in fact exactly the tangent space of X at P dual. I need to specify that this is taken at P. And so this means that our sheaf deserves the name cotangent sheaf. So now back to the proof of the theorem. If this sheaf is locally free of rank n, then all these vector spaces will have dimension n. So then the dimension of TPX will be n. So therefore X is smooth at P. But P was an arbitrary point, so therefore X is smooth. In the other direction, assume that X is smooth at P. So that the rank of the Jacobian dfi dxj at P is r minus n. We know this from the smoothness lecture. But this means that dx1 to dxn generate the tangent space, or rather the cotangent space. So what I'm doing here is I am saying that since the rank is r minus n, I can assume without loss of generality that it is the first n that span the tangent space, or if you wish, that the bottom right r minus n part of the matrix has determinant 0. So the determinant of the last r minus n squares, rows and columns is different from 0, not 0. But this condition is open. So this means that dx1 to dxn not only will generate txp, but they will generate txq. Check for all q in the open set U where this holds around P. And this is indeed an open condition, so this will be an open set. But what does this mean? This means that dx1 to dxn generate the space of the module of sections over U. Now, we know that the dimension of the tangent space is not smaller than n. And so if it's generated by dx1 to dxn, it is not greater than n. So this means that this is indeed a basis of this. In other words, we know that omega x at U is generated, or is the free module generated by dx1 to dxn. And this is exactly the statement that omega x is locally free of rank n, because we can do this for any point P, finding a neighborhood around P. So indeed, the cotangent bundle is useful. Cotangent bundle and tangent bundle are other names for the cotangent sheaf and tangent sheaf. Now let's see how to compute this in interesting cases. So remember from our discussion of Kähler differentials that we had this sequence, the so-called conormal exact sequence. And we want to globalize this, and this turns out to be straightforwardly done. So the proposition is that if you have a variety y over algebraically closed field K, and X a closed subvariety with corresponding ideal sheaf J, then there is an exact sequence J mod J squared into the pullback of omega yk into omega xk of X sheaves, of modules. I won't say too much about this sequence in this generality and the maps here, but two things I want to say. If you take affines, then you will find that with the appropriate notation, this becomes exactly this. The second thing is that both these sequences lack left exactness. What you ideally want is a sequence that looks like this. But for this to happen, you have to have enough smoothness or regularity somehow to make this happen. This is a general philosophy. One example when this is exact is if you take the inclusion of a degree d hypersurface in projective space over an algebraically closed field of characteristic 0. Then the conormal sequence is the following exact sequence. So pause and think how this is related to the previous sequence. Well, the rightmost term and the middle term are verbatim what we had here. But the first term here is J mod J squared. And here it is the twisted sheaf of X, where we take minus d with d, the degree of the hypersurface. So how does this come about? Well, what is this thing? So OX of minus d was defined to be I star of OPN of minus d, where I is the inclusion of X into Pn. And if X is irreducible, let's restrict to that case, then this OPN minus d, it's an exercise for you to show that this is the ideal sheaf corresponding to this embedding. We're getting closer to why this is J mod J squared. So this is the J we are looking for. So this is the J from the previous slide, the J, the ideal sheaf corresponding to the embedding. But why is this J mod J squared? Well, look in the affine setting. So take an affine open U in Pn. So maybe this is spec R. Then you get an honest ideal J that defines X. But then what we need to show is that this pullback is exactly this thing. But what is this pullback? The pullback takes J as an ideal in R, modulo over R, and tensors it over R with R mod J. This is exactly J mod J squared. You can check that mapping a tensor, the class of a tensor, the class of A tensor B, to the class of AB does the trick. So this is indeed what the conormal sequence says. And this helps us compute omega x provided we know omega Pn. But before we do that, let's look at what these maps are. So the map here takes phi and maps it to the differential of phi f. Here what is f? So f is the generator of the ideal of x. It is a homogeneous polynomial of degree d. And here I take d psi and map it to d psi considered as something over x. I leave it to you as an exercise to show that these are well defined and make the sequence exact. So how do we compute omega pn? Well, for that we have the Euler sequence. So omega pn fits here at the beginning of the sequence. Here we have the direct sum of n plus 1 copies of this twisted sheaf, and here we have OPN. So what are these maps, f and g? Well, f maps something here, so something here can be built from dxi divided by xj, and we want to map it to the following thing. In position I, we put 1 over xj. And in position j, we put minus xi divided by xj squared. This is inspired by the derivative rule, so the quotient rule from calculus, or the Leibniz rule that we have for these differentials, that says that dxi divided by xj is 1 over xj dxi minus xi divided by xj squared dxj. At any rate, we define this map in this way, and we define g as taking phi 0 to phi n into phi naught x naught plus etc. phi n x n. This does away with the minus 1 and gives us something in OPN. I'll leave it up to you to show that these are well defined and make this sequence exact. And so now we can compute the cotangent bundle of projective space and therefore of hypersurfaces, and there are other examples one can compute too. From the Euler sequence, by dualizing it, I can get something that tells me what the tangent bundle is directly. I can also take exterior powers to get the so-called canonical bundle or determinant bundle or whatever you might call it. But this is a bit too much for this lecture, and we will not have time to do these things, unfortunately. So we'll stop here, and hopefully this has convinced you that the tangent sheaves and tangent bundles and cotangent bundles are interesting objects that can be understood better in this current framework.